If you look at nature, there are some stunning colour effects. Rainbows are amazing things. Stunningly bright, vivid butterflies from South America. Dragonflies, how do they achieve those gorgeous greens? We just need to know. If you take a butterfly and you look at its wing scales, it's got very tiny wing scales, about 50 microns by 100. We found that within the wing scale, which is more or less fingernail material, the butterfly had created tiny sculpted structures, nanostructures, which gave interference, which gave diffraction. Those effects combined can give you a variety of different vivid colour effects. From the electron microscope images, we discovered an intricate structure in the wing scale of the morpho butterfly. And what we decided to do was to replicate that on a much larger scale. Here we have a structure corresponding to the scale of the wavelength of microwaves, with detailed ridges and with these Christmas tree structures internally. Then when we shine microwaves at this, it responds like light does to the butterfly wing scale. By unravelling the butterflies, we discovered a whole raft of new metamaterial type structures. If you structure matter on a fine enough scale, it doesn't respond in the simple way like a bucket of water or a piece of aluminium. It has new properties, new optical properties, new properties for different wavelengths. There was a fascinating paper by some South African scientists who were looking at a particular moth. It's got a metallic gold spot on its wing, and it turns out that it uses a zigzag grating, which is just basically a grating, and you zigzag it. Zigzag gratings haven't really been studied before, and they're fascinating. They have weird polarization properties, odd diffraction properties. We then make zigzag gratings, we then metallize them, and they have very interesting optical diffractive properties. If flat silver is placed into the scatterometer, all we would see is reflected green light. If we pattern the silver surface with a grating, then what we see on the screen is some missing portions of light. The light has gone into exciting surface plasmons. Scaling up from the visible to microwaves, we make samples of this kind. These scatter microwaves as the butterfly wings scatter light, but if we now metallize these, they will have very different properties which you would not achieve in a butterfly wing scale. They will reflect microwaves in particular directions. They will stop certain frequencies of microwaves. You can even make lighthouses, if you like, of microwaves, so you can steer them around. This is useful in a variety of applications, one of which is in RFID tagging. RFID tags are going to be placed on many objects to keep records of where they are, stock checking, movement of goods, drugs, blood samples, etc. Conventional RFID tagging, the success rate of monitoring a large number of RFID tags can be as low as 70–75%. By using these structured metal surfaces, we've raised that success rate to well above 99.9%, which is really a massive improvement. Our most recent work is to combine the patterned metal surfaces and the surface waves they have with some of these new ideas in what are called transformation optics, theoretical developments in recent years, where you take an ordinary optical design and you use a new mathematical approach to design new types of structures. And one of the things we're playing with most recently is an object called a Lundberg lens on a surface, which if you shine a surface wave, which is a plane wave at the lens, it focuses it to the point on the circumference of the lens. I go around from place to place talking about physics, and I find that from 3-year-olds to 93-year-olds, they're still fascinated. How does it all work? That's it, isn't it? How does it all work?